Hello, and welcome to the podcast of the pH of salts. So before we can figure out the pH of the salts, we need to figure out how to categorize salts. And there are recordings already made on the categorization podcast that really go through step by step how to categorize. But let's just review quickly. So here are a list of the pH spectators. We have the cations and the anions. The cations are going to include all of the first and second group metal ions. So I haven't listed all of them. That's why I did the ... But these are the major ones you're going to see. And most of the time, honestly, you're going to see sodium and potassium because they're the most commonly used. If we come down here to the list of anions, it's a very specific set of 5. Cl minus, Br minus, I minus, NO3 minus, ClO4 minus. And remember, they come from the strong acids. They are no surprise. So in order to decide what you have, you need to split up it into the cation and the anion. So for Kf, you have K plus, F minus. If we look on the list, K plus is a spectator, F minus, not on the list. We can't cross it out. When you're left with just an anion, that means you're going to have a basic salt. And the reason why you have a basic salt is because F minus is a conjugate base of HF. All right, so let's do the next one. NH4 Cl, so we're going to have NH4 plus Cl. Oops, doesn't want to write. Okay, we've got Cl minus. And so Cl minus is on the pH spectator list. NH4 is not. Okay, and so since this is cation, this is going to be a acidic salt. And the reason why it's going to be an acidic salt is because this is a conjugate acid of NH3. All right. Come down here, split this up, and I think I'm going to write this underneath of here. We're going to have Na, just because I'm running out of room over there, ClO4 minus. This is on the spectator list, and if we look, ClO4 is on that list, so we can also cross this out. So this would be a neutral salt. Okay, and here I'm going to break these up just right where they are so that I don't have to rewrite them. So if we look at the next one, we've got CH3, blah, 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 blah. This is going to be the plus. This is going to be the minus. We know that NO3 is a pH spectator, so we'll cross that off. We're left with a cation. So this is going to be a acidic salt. And it's going to be an acidic salt because this is a conjugate acid. Ca stands for conjugate acid. All right, the next one, we've got K plus, Br minus. Let me switch colors so we can see a little bit better here. So K plus, Br minus, K plus spectator, Br minus, also on the spectator list. That means you have a neutral salt. And when you have a neutral salt, you don't have to do any pH calculations. It's 7. All right, come down here. This looks a little bit weird. Well, we know that if nothing else, Na has to be Na plus, and all of this stuff has to be minus. We know that Na is a spectator. If we're left with an anion, that means it has to be a basic salt. And this whole thing here has to be a conjugate base. And it actually belongs to benzoic acid, so this would actually be the benzoate ion. This is sodium benzoate. You don't have to know that. I'm just letting you know. All right, so let's actually look at a practice problem. We have 0.4 molar NaCN. All right, so we have to figure out what we have first. So we're going to do it the quick way. We're going to put Na plus, Cn minus. Na plus, we're going to cross out, it's a spectator. Cn minus, not a spectator. All right, so what happens with the Cn minus, and this is the reason why we call it a conjugate base, is when we add it to water, it's going to act like a weak base. And we know all weak bases, we need to add water because it needs something to seal a proton away from. Now, everything happens in water. Just in some reactions, we have to write it. In some dissociations, we do. And in other ones, it's not as necessary. So for this one, we need it. Okay. And if you're having trouble with the dissociation of weak bases or acids, you can go back and watch the previous podcast. But basically, if this is a base, a weak base, it's going to pick up an H plus from the water. We can kind of think of water as H plus and OH minus. So it's going to pick up an H plus, and the two of them together are going to make HCN. And what's left over from the water is going to be the OH minus, which is our other product, okay? So we end up with these. But with any weak base or any weak acid, either one, most of it is going to stay in its original form. So most of it is going to stay CN minus. Very little of this or this is going to form. Okay, so how much of that forms is important because that's going to determine the pH of our solution. And in order to do that, we're going to need to write a Kb. Why is this a Kb? Because it's a base. Okay, so we're going to write the Kb. But before we write the Kb, we have a problem. When I go to look up the Kb value on the chart, there is no Kb for Cn minus. So what I'm going to need to do is figure out the Kb from the Ka. And so there's an equation that says that the Ka times the Kb equals Kw. And so we can use that and we can say, okay, Kw over Ka will give me my Kb. Kw is always equal to 1 times 10 to the negative 14th. My Ka for this, I'm going to look it up on the chart. And the Ka value that I'm looking it up for is this Ka, because this is the weak acid of this conjugate base. So the Ka value that I look up for this one on the chart is 6.2 times 10 to the negative 10. All right, and so we're going to plug this in the calculator and solve for our Kb. This is going to equal 1.6 times 10 to the negative 5. All right, so now we have our Kb value. We solve this like any weak base. And our first step is going to be to set up an ice chart. So we know the molarity of our base is 0.4, because that was given to us, again, right here. It's given to us in the problem. These are always initially 0. You're going to break some of this up with the water. We don't list the water because there's plenty of water to go around. Plus x. So this is going to approximate to 0.4 x. That's x. And so now we can go back and plug this into our Kb. So we know that the Kb is equal to the HCN OH minus. That's what makes it a Kb, is that OH in the numerator, and then over Cn minus. Okay, and that's equal to the 1.6 times 10 to the negative 5, and we're going to plug in x squared over 0.4, and these values are coming from this chart right here. So we go back, and now we're going to solve for x squared, or x rather. And our value for x is, let's see, x equals 0.0. I'm going to kind of make like a little box here just so that we don't get confused with our numbers. 0 to 5. And the importance of this is that x is equal to the molarity of the OH minus. Okay, so in order to find the POH, because remember when we have a base we always find POH, we're going to take the negative log, so we find the POH. Okay, so the POH, it wrote really big there, is going to be 2.6, and so we're going to end up, we subtract that from 14, we get the pH is going to be equal to 11.4, and that would be our final answer. All right, let's try to get one more practice problem in here. Oops, it just ran through the whole ice chart. Okay, there we go. We've got our problem back. Okay, so let's see what we've got here. So if we look at this problem, we have we can make this a we can make this a plus, this a minus. Okay, and so we know the Cl minus is a spectator. We are left with a cation, so this means this is going to be an acidic salt. And this is my conjugate, because salts always contain a conjugate, my conjugate acid. And we know that once we put this into water, it's going to have a chemical reaction with the water. It's going to have a dissociation reaction. And all of this is a lot to write. So what I'm going to do is I'm going to substitute all of this for BH plus. That's always our symbol for a conjugate acid. And we know that conjugate acids do what all acids do. They break up into an H plus. So we've got here our conjugate acid. It's going to reform the weak base that it came from, and it's going to generate an H plus. And that H plus we're going to circle because that's what's going to dictate the pH of our solution. All right, so for this, we're going to need to find a Ka value. And we have to have a Ka value because we have a acid. So when I go to look this up, there is no value for this on the Ka table. But I can use the Kb value for my weak base and convert it into a Ka. So we're going to use the equation Kb. Oops, we're going to use the Ka version. So the Ka is equal to Kw over Kb. And we know Kw is 1 times 10 to the negative 14. We're going to be super careful putting that in the calculator if we're using the E button. And the Kb for this we look up. So it turns out you don't actually have the Kb on your chart, but when I Google it, I am getting 6.3. So if you were trying to solve this one, you might have kind of got a little bit stuck there because it was not on your equation sheet, or on your chart rather. Okay, so now we're going to plug this into the calculator. Okay, and again, it's really important when you go to put this into the calculator, this right here, you're putting in 1E negative 14. And obviously for this one, you would put in 6.3E. Just make sure you don't, for this one here, make sure you don't put in 10E because it's going to mess up your calculations if you use that E button. Okay, so when we solve for this, we're going to end up with our Ka being equal to 1.59 times 10 to the negative 10. And we know that our Ka is going to be equal to Rb, which is our weak base, times H plus over BH plus, which is our conjugate acid. I'm going to run out of room here in a second. And in order to plug in these values, we would need to know our ice chart. So if we go back and we look at our molarity, it's 0.05. That's a 5. Okay, sorry, I went a little bit ahead of myself here. So this is going to be 0 and 0 initially. This is going to be minus x plus x plus x, and this will approximate to 0.05, and then these are x and x. We go back here. For these, we're going to plug in x, x, and 0.5, and we're going to solve for x. Okay, and that's 0.05. And so I am completely out of room, so I'm just going to go ahead and put it right into the calculator. So I found x was 2.82 times 10 to the negative 6, and I took the negative log of that. So I'm going to get pH is equal to 5.55. And I'll put up more practice problems in the next example. Thank you.